in the last few years, I've been thinking quite a bit about ethical and social issues in the use of machine learning and algorithmic decision making more generally. And I also saw that there's some discussion or a panel about sort of competition and marketplace questions introduced by machine learning. I hope to make some less technical remarks about that because I think there's less scientific to say there, but a lot of interesting things to discuss. And also relatedly, topics related to consumer protection and abuses by machine learning and AI. And so what I just want to do with my time is make some informal remarks, provide some personal opinions on these topics based on my own experiences and research, and you know, hopefully cue things up for the next couple of days for the rest of the speakers. As the last speaker mentioned, there's been a lot of discussion, really not first in the technical community, but first in the mainstream media and society at large, about the many things that can go wrong when applying machine learning and AI and related methods to algorithmic decision making. And before I describe, let's say a little bit more about what can go wrong and what we might hope to do about it scientifically, I thought I'd start by sort of just framing how things can go wrong in the first place. And so one thing you might wonder is, you know, if there's a lending model or consumer credit scoring model that exhibits racial bias, for instance, or there's some data analysis or machine learning methodology that leaks personal private consumer data, you know, you might, it's a reasonable thing to wonder whether this happens through active malfeasance. You know, are there evil programmers at tech companies who, you know, put in a line in their code that says if the person's race is this, then do this. If it's some other race, then do something else. Or whether they program backdoors into their code that permit privacy leaks. And there's good news and bad news here. My strong belief, and I think those of people who work in the field would say that no, there's absolutely no such malfeasance going on by evil programmers at technology and other companies. So that's the good news. The bad news is that the truth might actually be a little bit worse, which is these sort of collateral damage or consequences are actually the natural byproduct of applying, you know, the formal fundamental scientific principles of machine learning and AI, and I'll say a little bit more about that. The vast majority of what I think we would call algorithmic decision making is actually a little bit more specifically almost always driven by machine learning these days. So in particular, when you think about the algorithms that make things like lending decisions or decide what ads to show you on Facebook or Google, these generally are not what you should think of as hand-coded or programmed algorithms, but rather they're the result of taking data, you know, historical data, whatever that might mean in a given domain, giving it to an algorithm, and that algorithm, of course, trains a model on the data, and then at the end of the day, it's the model that's actually making the decisions. It's the model that's actually deployed in the field. And typically, the algorithm that transforms the data into a model is actually tremendously simple and very principled from a scientific standpoint. So if I had slides, one thing I like to do in forums like this is put up the Wikipedia pseudocode for the so-called backpropagation algorithm for neural networks, which the previous speaker mentioned. And that pseudocode is literally a simple loop with about 10 lines of code in it. And a real working version of it wouldn't be that much more complicated. And it's doing the most obvious thing you can possibly imagine, which is essentially going through the training data and adjusting the parameters or knobs of the model in order to minimize some, you know, usually accuracy or error-based cost function, okay? So that algorithm is not opaque at all. It's entirely transparent. Sometimes, you know, when I talk to people who aren't in the field, they naturally assume that machine learning algorithms, you know, the code for them might look like something like I imagine the code to a video game like Grand Theft Auto looking, you know, hundreds of thousands of lines of spaghetti code with all these special cases and details, and it's not like that. So then the natural question to ask next is, you know, if the complexity doesn't lie in the algorithms themselves, then where does the complexity creep in? And of course, it's from the interaction of the data being processed to produce a model mediated by these very, very simple algorithms, okay? And so the problems arise these days not so much from the algorithms themselves, which again are very simple and operating on very basic well-motivated scientific principles. The problem is really when you work in extremely large, complicated model spaces, of which deep learning is just one and perhaps the most recent example. The sort of space of models has a lot of sharp corners in it, as I might put it, which allow you to kind of optimize the thing that you're trying to optimize, like minimizing the error on the data, at the expense of other things that you didn't explicitly ask for, like fairness or privacy. And I think if there's one kind of important adage to understand about machine learning, it's that basically modern machine learning will not give you for free anything that you don't ask for and specify. And in general, you shouldn't expect it to avoid things that you don't want, that you didn't tell it you didn't want. Okay? And this is, I think, the source of a lot of the kind of violations of social norms and values that we've seen by machine learning and AI in recent years. So that's a little bit about what can go wrong. Now let me talk a little bit about, that's a little bit about how things can go wrong. And sort of with that background, I want to talk about, well, what are the different things that can go wrong? And most importantly, what can we do about them from a kind of scientific standpoint? So, the things that can go wrong are things that I've mentioned already, which is violations of things like privacy or fairness or interpretability and transparency, or even safety or morality, if you like. The sort of logical extreme of this, for those of you who've heard of it, is this sort of parlor game or science fiction thought experiment known as the Singularity, in which AI, AI achieves superhuman intelligence to the point that, for lack of a better term, the robots become our overlords. While that's a fun thing to think about, I don't know many sane people in the machine learning community who actually think that that's our sort of gravest technological risk anytime soon. All you need to do is kind of see what AI and machine learning can actually achieve right now and compare it to humans or other biological species, and you will be deeply underwhelmed by what we can accomplish so far. But violations of social norms are like already with us now today, and on a very large scale, whether we know it or not, or whether we're measuring them properly or not. I think it's important to say to this audience that I think I and many of my colleagues, we do believe that better laws and better regulations are possible and should be developed, and I'm sure that that's being worked on and is a necessary activity. But I think my opinion is that will be woefully inefficient in the algorithmic era to actually keep up with the types of violations of social values that we're seeing, because basically human organizations don't scale, and you can't sort of expect to police the sort of violations I'm talking about with sort of regulatory agencies that are poring over the decisions made by algorithms on sort of a human timescale and hope to keep up. So an alternative approach, which I'm a great advocate of, and as are a growing number of people who do technical work in these areas, is to design better behaved algorithms in the first place, and to actually endogenize various notions of social norms inside of our algorithms, and asking that our algorithms, that the actual code obey some definition of privacy, some definition of fairness, some definition of morality, if you like. And of course, this leads immediately to two very difficult questions. The first difficult question is, how do you define these things, as the last speaker said? How do you define algorithmic fairness? How do you define algorithmic privacy? And then if and when you can come up with such a definition, it's going to come at some cost, right? So if I have some notion of fairness in models that are used to provide criminal sentencing guidelines, my asking for fairness from that model by gender or race will come at a cost of accuracy. What I'm saying is like a tautology. If I ask myself to find the model in some space of models which minimizes the error, period, and then I ask to find the model that minimizes the error subject to your favorite definition of fairness, the error can only get worse. And so in a model like, let's say in a setting like criminal sentencing, this means that a cost to accuracy might mean sort of, hard things to think about. It might mean incarcerating more innocent people, or it might mean letting more guilty people go free. So there will be societal and technical costs to imposing these sorts of constraints on our algorithms. But I think my view and the view of many people in the field is that we have to go down this road. We have to design algorithms that incorporate these values. We have to talk about what the possible definitions for these values are. And we need to study these trade-offs between the thing that people normally optimize for in machine learning, which is accuracy, and the trade-offs to different social norms. Okay, and so what I want to do with most of my remaining time is just tell you a little bit about the sort of very active research that's going on in the computer science and machine learning and related communities on this scientific agenda, sort of picking definitions for different social values or norms and actually encoding those norms inside of our algorithms and then trying to study what the trade-offs will be with things like accuracy and other more standard objectives. So let me first talk about sort of the work that goes on in the area of privacy in machine learning, and not just in machine learning, but more generally in kind of data analysis and data science. And I think it's helpful to say just a little bit about the distinction between what I'm thinking of as privacy and a closely related and complementary area, which is that of security and cryptography. So security and cryptography, to a first approximation, is a technology about keeping data locked down. It's about controlling access to data and making sure that people who shouldn't have access to data don't get that access by basically hacking into a system that they shouldn't hack into. And this is largely the domain of security and cryptography. And that's one notion of privacy. That's sort of control of your data and making sure it doesn't get accessed or stolen by people who shouldn't. Here I'm talking about something a little bit different and more nuanced, but in many ways is equally as pervasive and important as notions of security, which is the fact that you have all this data that's being collected by different companies and agencies and other organizations, and you might worry about what not just sort of who's accessing that data, but what can be inferred about you from that data that isn't directly in the data itself. So the kind of thing that I'm concerned about here is that if your medical record is used as part of a study to build a predictive model, let's say, for some disease based on symptoms, and then that model is published or used in the field, could it be that the use of that model or the publication of that model, perhaps combined with other publicly available data sets, actually reveals a great deal about your own personal medical status and record? Okay, and if you go down the road of thinking about possible technical definitions of this type of privacy, I believe that most of you would eventually come to two kind of, I think, important conclusions or desiderata from any sort of privacy definition for machine learning or data science. One is that you need to account for the fact that any particular data set that you want to keep private in some technical sense will not be the only data set in the world. And in particular, that data set might be combined with other data sets that you don't know about or didn't foresee or don't even exist yet but might exist in the future. And one consequence of this that I will state without proof is that this means that any definition of privacy that involves anonymization is essentially a flawed definition of privacy, right? Because anonymization refers to taking the data set that's in front of you and doing things like eradicating personally identifiable information. But the literature and news is, rife with examples where you anonymized one data set, somebody else anonymized a second data set, those two data sets were combined and then maybe combined with some publicly available information, and your specific data could be backed out of that. You could be, as we like to say, re-identified, or the data set could be de-anonymized, as they say. And I think many people feel strongly enough about this assertion that there's sort of a saying in the field which is, anonymized data isn't. meaning that whatever you think you did to de-identify individual identity in a data set, that can often be undone through the unforeseen combination of that data set with other data sets. The other, I think, sort of axiom for any definition of privacy that's important is that in order to have a definition of privacy that still allows us to do anything useful with data, it's important to isolate the potential harm that comes to somebody as the result of the use of their data in some analysis or model building exercise versus the harm that might come to them just because data analysis reveals some facts about the world. So for instance, if you were a smoker in the early 1950s, before there was discovered a link between smoking and lung cancer, well, when somebody did data analysis and discovered that there was a strong correlation between lung cancer and smoking, and you were a smoker, that fact does harm to you, but it doesn't matter whether your data was used in that analysis or not, right? Researchers were going to discover this fact whether your particular data was used or not, and a harm was done to you by the fact that suddenly it's revealed that smoking is bad for your health and you are a smoker and everybody knows it. But that harm was not done to you specifically as a result of the data analysis using your data or not. You were basically, this harm was going to be done to you whether your particular medical record went into those studies or not. And so there's a very rich definition of data privacy known as differential privacy that was introduced about 15 years ago and has received a great deal of scientific attention in the interim, and now has a very rich theory and a very rich body of algorithms that basically, on the one hand, meet this sort of very strong notion of data privacy, which has to foresee the possibility of triangulation through the combination of multiple data sets on the one hand, but still permits sort of powerful use of data. And so, one kind of pseudo theorem that I will state to you is that everything that we pretty much know how to do today in machine learning, we also know how to do in a differentially private way, and it's just a matter of companies adopting this technology and choosing to do their machine learning and data analysis in a differentially private way. And we're actually starting to see large-scale deployments. Both Google and Apple use differential privacy in meaningful large-scale ways in some of their services, and maybe more importantly, the 2020 US Census, every single statistic or report that they release as the result of the 2020 census, they are planning to do so under the constraint of differential privacy. And so this is an example, I think, of a very promising kind of case study, right? Of course, people have thought about different definitions of privacy and data analysis and machine learning for a long time. There was a struggle to kind of come up with the right definition. Many of us believe that sort of definitions based on anonymization are fundamentally flawed, but then a better definition came along around 15 years ago. There's been a huge amount of research on this particular definition, and the good news is that for this particular definition of privacy and this particular social norm, it is possible to sort of give these very powerful guarantees at not too great a cost to accuracy or computational efficiency and the like. We can sort of, have the best of both worlds, if you like. So let me say a few words about research in fairness in machine learning and algorithmic decision making, which is much more recent. It's a much more nascent field than the study of privacy in machine learning and AI. But we already know a fair amount about it, and one of the things we already know about it is that it's going to be a little bit messier than privacy. So my claim is that if you waded into these literatures and you looked at the work that's gone on in differential privacy and looked in particular at the definition of differential privacy, you perhaps, like many people, might sort of agree that this is sort of the right definition of privacy. So we already know that there's not going to be a right definition of fairness in algorithmic decision making and machine learning. And what do I mean by we know there's not going to be a right definition? So there's already, from the last several years, several examples, several papers which have results of the following form. They basically say, well, whatever your definition of fairness is, wouldn't we all agree you'd want it to have at least the following 3 properties? And you kind of look at those 3 properties and you say, yes, yes, I would definitely want any definition of fairness to at least meet those 3 properties, and probably other stuff too. And then, of course, the punchline of these papers is, well, guess what? Here's a theorem proving to you that you cannot simultaneously achieve all 3 of those properties in any definition of fairness. Okay, so those of you that have a kind of economics or social choice background might know about like Arrow's impossibility theorems for sort of voting systems. These have a very similar flavor. And so this has very concrete consequences. So in particular, a typical notion of fairness in machine learning would ask for the approximate equality of false positive or false negative rates across different groups. So let me give an example. Suppose you're a mortgage company and you're trying to build a statistical model that tries to predict from people's loan applications and credit history whether they will repay a loan if you give it to them or not. Okay? Very natural thing to want to do. And you want this model so that when people apply, you can make a prediction about whether they'll repay or not, and then you want to give loans to people that will repay you and not give loans to people that you predict won't repay you. But because this is a statistical model, you're going to make mistakes. You're going to have both false positives and false negatives, right? And we might think of false negatives as really the case that causes harm to the consumer in question, right? False negative being somebody who's creditworthy would have repaid the loan if you didn't give it to them, but you decided to reject them, okay? So we might think of false negatives as a harm inflicted on a consumer, and false positives are sort of the people that got lucky. So a typical definition of fairness would basically say that, look, you're going to make false rejections. We're not going to try to prevent that. But across different racial groups, it cannot be the case that the false rejections rate differ wildly. It cannot be the case that the rate at which you falsely reject qualified African American applicants is 3 times the rate at which you falsely reject qualified white applicants. Okay, so this is a very natural constraint. And these impossibility theorems basically say if you ask for that and you also ask for equality of false positives, i.e. that people got lucky, and one other related condition, you cannot simultaneously achieve all of these. So what this means is that we already know that in fairness we're going to have to simultaneously entertain multiple competing definitions of fairness. And so not only will there be sort of trade-offs and competition between fairness and accuracy, there's even going to be competition between different notions of fairness. If you optimize for one notion of fairness or constrain for one notion of fairness, you might be damaging or losing on another notion of fairness. Okay? But nevertheless, we know this and we have to proceed anyway. And so there's been a great deal of research in the last several years on algorithmic fairness and on different notions of fairness and what the trade-offs between that particular notion of fairness and accuracy is. And this is an area where, to again echo something the previous speaker said, when you sort of talk about the potential interfaces between technical people and policymakers and other stakeholders, I think there are very, very good starting points. So one thing you can do, for instance, is if you pick a particular definition of fairness, like approximate equality of false rejections in a lending application, and you have a data set in front of you, a historical data set of people who did and didn't repay loans, you can actually trace out empirically. I would have shown this slide if I'd met the deadline. I can actually show you an empirical trade-off where on the x-axis would be the predictive error of your model. On the y-axis would be a numerical measure of the extent to which you violated this fairness notion. So 5% would mean, sort of 5% unfairness means that, let's say, between African Americans and other races, there's as much as a 5% disparity in the false rejection rates. And I can just trace out a curve for you that shows you the menu of choices you have. So you can get the lowest error, but if you sort of ignore fairness entirely, that'll give you the lowest error, but it'll give you the worst unfairness. At the other extreme, I can demand that the false rejection rates differ by 0% across populations. It's a very strong constraint. And I will get the worst error, but the most fairness, and in between you'll get something in between. And I think this is the type of, sort of quantification of the tensions that we face as a society in making these kinds of decisions, that's the right, at least initial interface between, people like me and people like you, for lack of a better term, right? Because it sort of really shows starkly the choices that you have available. Just to say a little bit more about fairness, most definitions of fairness, like the ones I've been discussing, actually only hold at the group or aggregate level. So you're only making promises to sort of groups of people in a statistical sense, and you're not making promises to individuals. So, sort of more prosaically, if you are, if you're a person of a particular race that was falsely rejected for a loan, you would have repaid that loan. The consolation that you have in these types of definitions is like, well, we're also rejecting people from other races who would have repaid their loans at the same rate that we're rejecting people from your race, which is sort of cold comfort if you're somebody who was mistreated in this way. And so a lot of recent research, including some of my own, is it trying to move towards definitions of fairness and studying their algorithmic implications that try to make finer grained promises, maybe not all the way down at the individual level, but to much finer grained groups than just things like, race, top level race or gender or the like. So these are two social values, privacy and fairness, on which in relative terms we know quite a bit already scientifically, and I think we're well on the way to kind of developing both a science and an engineering of designing better algorithms and understanding what the trade-offs are between accuracy and the various definitions of the social values that we've come up with. My former grad student and colleague Jen Wortman-Vaughan is giving the keynote tomorrow, and she's done a lot of recent research on interpretability and transparency in machine learning, which is another, of course, important social norm. I think we know a lot less there so far, partly because we just haven't had as much time. But one of the problems with sort of coming up with satisfying definitions of things like transparency and interpretability is that there's fundamentally an observer in kind of the middle of such a phenomenon, right? So when you talk about interpretability, for instance, of a statistical model, you have to talk about interpretability to whom and for what reason, and in particular, the sort of numeracy of the audience you have in mind will matter greatly, right? If we're talking about interpretability to people with like a statistics training, that means one thing. If we're talking about interpretability to the average American citizen, well, the average American citizen has not been exposed to linear regression and may find it a little bit bewildering to even talk at all about an abstract mathematical mapping from loan applications to lending decisions. And so I think much of the research that needs to happen on that topic will have to have like a cognitive and behavioral element to it. You'll need to do human subject studies with the type of audience that you're interested in and ask them what they think is interpretable to them or whether you can explain models to them and the like. So I'm almost about out of time, but just to sort of quickly touch on a couple of other things that I saw on the agenda. I saw that there was there was one panel title that had a very intriguing name, which was Algorithmic Collusion, and I'm not sure exactly what the context that's meant there is, but if the concern is that we might be entering an era where algorithmic decision making causes in some implicit or explicit kind of large-scale way collusion between different entities, whether it's on things like pricing or decision making or the like, I definitely think this is already happening. One area in which I'm very familiar with this already is on Wall Street, where quantitative trading teams tried to build statistical models to predict the directional movement of stocks and, so to speak, beat the market. And my basic belief there is that there's a huge amount of implicit collusion going on there. And it's really because, when we all use the same or similar data sets, and when we all use the same or similar algorithms to train our models, then even if we think we're clever and independent and creative, we are going to be strongly correlated just through the data, right? If we're trying to predict the same thing and we're using similar data sets and similar methods, then no matter what else we do, everything else we'll do is a second order effect from the fact that the data itself will correlate us. And so I think that that this is an interesting topic on which there's probably interesting scientific things to say, but I haven't thought about it yet, and I don't know of a large body of research on it.